Welcome dear students to St. Peter's College, Colombo, Fornigam branch, grade 12 physics. Today I am going to do unit 4, thermal physics, competence level 4.3 and 4.4. Gas laws. Now, when we are talking about gas laws, we have three gas laws: Charles' law, Boyles' law and pressure law. Before that, now the gas is a little bit different from the liquid and because the molecules can move here and there freely because they are intermolecular attraction. The forces are very weak. Therefore, they can move here and there so that they have no definite shape or a definite volume. So it takes the volume of the container and also the volume of the shape of the container. So when we think about a balloon, now I am blowing a balloon, right? So when I am blowing it little by little, the volume increases, and if I press it from my palm, then the pressure will increase. At the same time, there will be a small temperature rise. That means you can feel that pressure, temperature, volume are having connection with these gases. So we call these three properties are properties are macroscopic properties of gas. So from these macroscopic properties, we can explain the behavior of a gas, right? So using these three, our scientists built these three laws: Charles' law, Boyle's law and also the pressure law. They made one constant and checked the behavior of other two. And if you think about the air, our atmosphere, you have carbon dioxide, oxygen, methane, right? Sulfur dioxide, etc. So all these gases are different from each other. Their intermolecular bonds are not, the intermolecular forces are not equal, and also the atom sizes, the volume of the atoms are not equal. So if we neglect these two, the volume of the molecules and also the intermolecular attractions, the forces, they all behave like same. So we assume that this volume is negligible and also there are no intermolecular forces, and we introduce a gas called ideal gas. So let's see. Gas laws. The experimental relationship between the pressure, volume and temperature of gases were investigated and early experiment results and the laws called gas laws. Now, see, ideal gas. Gases are different from each other due to their intermolecular forces and attraction. If these two are neglected, all gases behave in the same way. A hypothetical gas whose molecules occupy negligible space and have no interactions and which consequently obeys the gas laws exactly are called ideal gases. Now, the first law, Boyle's law. For a fixed amount of mass, always the mass is fixed. For a fixed amount of mass of an ideal gas, it will be an ideal gas, at constant temperature, now we make temperature constant. Constant temperature, pressure is inversely proportional to the volume, inversely proportional. That means P is inversely proportional to 1 over V, right? Now, if we write the equation P1, V1, you can write P1, V1 equals constant, right? So, PV equals constant, okay? If PV is constant, if you draw the graph against P against V, then you will get a graph like this. And if you draw a graph P against 1 over V, you will get a straight line going to 0, 0 like this. Now, consider two instances. Now, somewhere you have a volume of mass V1 and the pressure is P1. That is P1 V1 equals constant according to Boyle's law. Some another place, the same gas, you have P2 and P2, the pressure P2 and P2, and that is also constant. So these two sides are equal, therefore you can write P1 V1 equals P2 V2. That is Boyle's law. And for different temperatures, now we said the temperature is constant. T1 is constant for the whole process, T2 is constant for the whole process. But T2 is greater than T1. If T2 is greater, the curve will be little upper than the T1. T1 is here, T2 is here. Right? PV curve. Then, see this example. Now here you have a small amount of gas trap. Here also you have a small amount of gas. The same thing, same gas, right? When it is vertical, the height is, right? When it is vertical, the height is 15 centimeters. And when it is horizontal, the volume is 20, the length is 21. You know, this cross-sectional area is, if we consider the cross-sectional area as A into 15 is the volume, right? Pressure is the atmospheric pressure plus the mercury column's pressure. Now this mercury column is 30, here also 30, right? Now look, let the atmospheric pressure be H centimeters of mercury and P be the density of mercury. Thus, P equals H rho G, right? When the tube is held vertically, pressure H plus 30, right? Atmospheric pressure plus this 30 into rho G, right? Volume 15 into cross-sectional area. For the second instant, the pressure of the air is H rho G because this column's weight won't come. It is horizontal. Gravity won't affect for this column, right? So, H rho G, only the atmospheric pressure, plus the volume 21 into A. So, P1 V1 equals P2 P2 for these two instances. We are applying Boyle's law, right? P1 V1 equals P2 V2. So you can write 15 H plus 30 equals 21 H. So from this you can find the H atmospheric pressure, right? Example 2. Here you do this. You try to do the same thing, right? Do this yourself. Now using Boyle's law, the experiment we are doing this experiment to determine the atmospheric pressure, right? Now you need look here, experiment to determine the atmospheric pressure. You need a quill tube, right? A quill tube like this, and a stand and a meter ruler to measure the heights, and also mercury, little small amount of mercury. So you insert a mercury to the quill tube, and you can trap an air column here. The length of the air column is simple L, and the quill tube's length is L, right? Capital A, H, simple H is the vertical height from the table top to the end of the quill tube, right? And simple L is the length of the air column, capital L is the length of the quill tube, and capital A is the cross-sectional area of this quill tube. Simple X is the length of the mercury column, rho is density of mercury, capital H is atmospheric pressure. Now we are going to determine the atmospheric pressure, capital H. Okay. According to Boyle's law, you know PV equals constant, so P equals constant K over V. H pressure is H sine theta rho G, right? Theta, here this angle is theta. Now H sine theta rho G. So P is H plus sine theta rho G equals K over AL. AL means the volume. Volume is cross-sectional area into the length of the air column. So applying this, you can simplify this like this way and draw a graph 1 over L versus H, right? So we are going to differ this height time to time and measure the height and also the length of the air column. Take 4-5 readings and plot a graph, and you will get a graph like this, right? So this will be the gradient and this is the intercept, right? So if you divide a gradient by intercept, you have to find the gradient, right? You know how to find the gradient from a linear graph, and also the intercept is this, right? If you divide the intercept by gradient, you will get this capital H equals intercept divided by gradient into x over capital L. You know the value of x and also the value of L, so that you know the intercept value and the gradient value, so that you can calculate capital H, right? Now, this is the procedure. You can go through this. These are the readings. You can get the height H, simple L, all in centimeters, and you need 1 over L to draw the graph, right? Here we are changing the H height so that it will come to the x-axis, and 1 over L will come to the y-axis, right? Length of the mercury column you have to measure, and also the length of the quill tube, right? Go through this note also, then you can find pressure law, right? Here, the pressure law states for a fixed mass of ideal gas at constant volume, the pressure P is directly proportional to the absolute temperature T. Okay, now P over T is constant. P over T is constant. So if you draw the P over T Kelvin temperature, you will get a linear graph going through 0, 0. If you draw the graph with Celsius degrees temperature with pressure, you will get a graph like this. This will cut the x-axis at minus 237 degrees Celsius. Okay, if you take two instances, P1 over T1 equals P2 over T2. As earlier, I explained you the Boyles law. Now, see this example. So, this I have used the pressure law, P over T equals constant, right? So, this is also very simple. The first instant, the temperature is 273 minus 17 plus 17, right? Second instant, 113 plus 5. So, you can calculate pressure here. See this one also. This is also a pressure law, P over T equals constant. A constant volume gas thermometer consists of a perfect gas at 17 degrees Celsius when the barometer shows 75 centimeters of Hg, right? Do you know a barometer? Which is the capillary tube invertedly dipped into a mercury, and the mercury column will give the atmospheric pressure. That is called a barometer, right? A perfect gas. At 17 degrees, when the barometer shows 75 centimeter of Hg, there is no difference of Hg levels. At 57 degrees Celsius, find the difference in Hg levels. Here, volume is constant, right? P over T equals K. Let P the pressure at the second instance. Okay, we have to find P. First, it is given that 75 centimeters HgCl. Second instance, P. First, it is 17, so that 273 plus 17, right? Second instance, 273 plus 57. We are adding this 273 to convert into Kelvin temperature, right? Now, here, look, the Celsius temperature, right? 75 over 290, PO over 330. We can subject P and find the pressure at the second instant. Look here, this is the second experiment to verify the relationship between the pressure and the absolute temperature of a gas at constant volume, right? Say, you need a instrument like this, the bulb here, right? The constant volume apparatus, right? And here this is a pressure gauge, or even you can fix a manometer here. Manometer is used to measure pressure, or a pressure gauge. And here you want a thermometer, a stirrer, a beaker, Bunsen burner, and a tripod, right? So you fill water up to here and dip the bulb inside the water, and you little by little increase the temperature, right? when you increase the temperature, you have to stir it also, because to get the temperature uniformly distributed among the water bath, and also to get the inside air heated, right? Uniformly heated. And then when the air inside the bulb get heated, the pressure increases and it will indicate here the pressure gauge. So that you can draw a graph P against T, and it will go, if it is Kelvin, as I told you earlier, it is going through 0, 0. If it is Celsius, it is cutting the x-axis at minus 273, right? Then this is the procedure. These are the readings. You have to get the temperature in Celsius, and you have to convert it into kelvins. If you are drawing the graph with Kelvin temperature, readings of the pressure gauge, right? Here, conclusion, as stated in the theory, according to the graph, the relationship between the pressure and the temperature of the gas at constant volume is verified. Note this, go through always this note, because this is very important. The temperature of the water in the heater should be raised very slowly, and the water should be continuously stirred, since the temperature of the air in the tube connecting the bulb and the gauge and the temperature of the air in the bulb do not exist at the same value. The resulting error can be minimized by a bulb with a large volume and a capillary tube as the connecting tube, right? Now, this is the Charles law, the third law, right? This law states that the volume of an ideal gas at constant pressure is directly proportional to the absolute temperature. V is proportional to T, right? V is proportional to T. That is the ratio. V over T is constant when the pressure is kept constant, okay? So, for two instances, here V1, T1, here V2, T2, you can say V1 over T1 equals V2 over T2. If you draw a graph, volume against temperature, you will get a straight line like this. And experiment to verify Charles' law. Now, this is an experiment to verify the above law, right? So, you need a narrow uniform glass tube with thin walls, right? Closed at one end and having a column of dry air trapped by an index of mercury at the closed end, right? 0 to 100 thermometer, a tall beak of water, a stirrer, a tripod, a wire gauze, a Bunsen burner, clamp, and a few rubber bands, and a scale calibered in millimeters, right? So, you fill the beaker up to this level, and you keep it on the Bunsen burner, and you insert the stirrer and the thermometer and the scale and the glass tube, right? That glass tube is having a mercury column, and you have trapped the air column here. Here also, when you increase the temperature, right, this water beaker get heated, at the same time the air column inside the tube also get heated, and it expands, and now you can measure the volume and also the temperature. After that, you can draw the graph, volume LA, that is L is constant, so you can get the length of the air column, and the temperature, you will get a graph like this. V is proportional to T, so that LAV is LA, right? Cross-sectional area into the length of the air column equals K into the temperature. So, L equals Ka over T. Okay, method, you know. And this is the procedure. These are the readings that you have to take, and conclusion, discussion, and the note. Look here, the note is very important. You go through this note also, right? Example from past paper 2015, right? See, now they have given the same thing here as the practical. See, this is the constant volume thermometer. Now you have the bulb here. Instead of the pressure gauge, they have fixed a manometer. This is also to measure the pressure. As I told you earlier, you can fix a pressure gauge or a manometer here, right? The experimental setup shown in the above figure is used to verify the pressure law for a gas, right? The pressure law can be applied to a gas only if the two variable quantities resisting in the gas are kept constant. What are these quantities, right? Look here. Madam, good morning. I have already started.
It's okay.
Here see the example, past paper question 2015, right? Here they have given the constant volume pressure thermometer, right? Now the experiment setup shown in the above figure used to verify the pressure for a gas. The pressure law can be applied to a gas only if two variable quantities pertaining to the gas are kept constant. What are those quantities? So they are asking what are the quantities that you are keeping constant here. The mass, obviously the mass is constant, and also the volume, right? So the next question, what is the reason for using the capillary tube XY in this setup, right? The XY capillary tube, this is the XY capillary tube, because to minimize the volume, here we have a constant volume here. So if the air flow to this area, that will disturb, right? So you want to keep this constant as this volume is negligible because this is a capillary tube, right? If not, the air will go to the tube also, that volume also you have to consider, right? Then explain why it is necessary to increase the temperature of the water bath slowly in this experiment. Because we have to increase the water bath's heat very slowly, because you want to distribute this equally among the whole bath, and you have to stir it also, and you have to get the same temperature inside this air also. There's air in this bulb, so you want to get heat this air also for the same temperature as the water bath, because we are getting the temperature from the outer water bath, right? So even if the temperature of the water is maintained at a certain value, it does not mean that the temperature of the gas inside the bulb has reached the same value. In this experiment, how would you make sure that the temperature of the gas inside the bulb has reached the temperature of the water? Because we are having a mercury column here. You see, there is a mercury column, and if you are keeping this position constant, we can say that is quite equal, right? Then go to the next one. Write down the two main steps used in the experiment procedure to maintain the temperature of water at a suitable value before measuring the temperature in this experiment. So there is a stirrer. You have to stir it continuously, and also here first I think you have to stir it constantly, and when you are taking the reading, when the thermometer is steady, you take out the Bunsen burner out and then take the readings. Okay. Then F part, write down the main steps in the experimental procedure that you would follow before taking the relevant readings to obtain the pressure of the gas, right? So you have to keep this always up to this indicator. If not, the pressure will be giving incorrect readings. So make sure this indicator, the mercury level is there in the indicator. Then, if the atmospheric pressure is capital H centimeters of mercury and the height difference of the two mercury levels of the tube A and B is H centimeters, draw a sketch of a graph that you would plot in the given diagram in order to verify the pressure law, right? So you have a graph here. So you have to label the axes here, the pressure axis and the temperature axis, and the graph will be a straight line going like this way, right? So you have to draw it and show. Then the H part, the graph below shows the variation of a pressure P with volume V for an ideal gas at temperature 400 Kelvin. Now look, this is 400 Kelvin PV graph, right? PV graph. So they are asking, calculate the values P1 and P2 of the pressures corresponding to the volume 20 into 10 to the power minus 3 m squared and 60 into 10 to the power minus 3 m squared of the gas at temperature 600 K. So you can use V over T, V1 over T1 equals V2 over T2, and P1 over T1 equals P2 over V2. Then combining this, you will get P1 V1 over T1 equals P2 V2 over T2. From that, you will calculate this, right? Okay. The last question. Mark the points corresponding to the values that you have obtained in H1 above on the graph given under simple H above, and draw a rough sketch of a curve to show the variation of the pressure with volume at 600 kelvins of the gas on the same graph. The same graph, you can mark this, obtain 2 points. Okay. Then this is also an example from the past paper 2018. So the same thing that I explained in the experiment, this is also there in the note. So I think you will be able to answer this question, right? Then ideal gas equation. The ideal gas law, also called the general gas equation, is the equation of a state of a hypothetical ideal gas. It is a good approximation of the behavior of many gases under many conditions, although it has several limitations. Ideal gas equation is the PV equals nRT, where P is pressure, V is the volume, N is amount of substance, R is the ideal gas constant, T is temperature. Now, where N is simple M mass divided by capital M molar mass, right? So therefore you can write PV equals M over capital M RT, and so you know, if you want density is M over V. That means density equals P M over RT, right? Then Avogadro hypothesis. So for any gas, the value is same. That value you have to calculate and get from the Avogadro's law. Avogadro's law states that the equal volume of all gases at the same temperature and pressure have the same number of molecules. From that, you can calculate this. According to Avogadro's law, mole of gas occupies 22.4 liters at standard temperature pressure. Here, V is 22.4. That is 22.4 into 10 to the power 3 m cube, and P is 760 H rho G, right? This is H rho G, then you will get 1.013 into 10 to the power minus 3, 10 to the power 5, and then you can calculate R is PV over T, that you substitute the values and you will get R equals 8.31 mole per Kelvin, right? This value is the same for all gases and it is called the universal gas constant. Now, this is also gas law, Dalton's law of partial pressure. Here, if you have number of gases, it says all the gases exerting pressure P1, P2, P3 like that. If you add all the pressure, that all pressures will, the sum of the pressures will be equal to the total pressure, right? If number of immiscible gases are enclosed in a container and individual pressures of these gases are denoted by P1, P2 and P3 and P4 like so on, then the total pressure in the container will be equal to the sum of the individual pressures of each gas, right? The total pressure will be the sum of these other gases. So ideal gas law is PV equals nRT. In terms of pressure, you can write, if you substitute pressure, you can see nRT over V, right? Dalton's law of partial pressure means P total equals P1 plus P2 plus P3 like this, and for instead of P1 you can apply N1RT V, N2RBT VT over V like that, right? Then pressure coefficient of gas beta, we denote as beta. Constant volume, at constant volume, the ratio of increase of pressure per 1 degree Celsius rise in temperature to its original pressure at 0 degrees Celsius is called the pressure coefficient of gas. Beta equals that certain temperature at that pressure at that certain temperature minus 0 degrees Celsius pressure divided by the 0 degrees temperature pressure into that temperature, where beta equals pressure coefficient of gas, right? Then combined gas equation, we can combine, derive this combined gas equation using the pressure law and the Charles law, right? Pressure law is this P1 over T1 equals P2 over T2, and Charles law is P1 over T1 equals P2 over T2. Then combining these two, you can derive this P1 over T1 equals P2 over T2. So we'll go to this example. At the top of a mountain, a manometer reads 7 degrees Celsius and barometer reading 70 centimeters of mercury. At the bottom of the mountain, they read 27 degrees and 76 of mercury respectively. Compare the densities of air at the top and the bottom. Densities, so instead of V, you can take D and M. M for both equal, therefore M won't come. P1 over D1, T1 equals P2 over D2, T2, right? Then apply the values, given values, and you will be able to get the ratio like this. Example, another one. The temperature at the bottom of a 40-meter deep lake is 12 degrees Celsius, and that at the surface is 35 degrees Celsius. An air bubble of volume 2 centimeter cube rises from the bottom to the surface. What will be its volume now? Atmospheric pressure is 10. So again you can use the combined gas law equation P1 V1 over T1 equals P2 V2 over T2. The first instant you have the volume this much, right? Second instant you have to find, that is V, and we consider it as V2. Then you subject V2, other all are known, so that you can get the answer. But you have to convert the Kelvin temperature to Celsius, centigrade temperature to a Kelvin temperature, right? And Van der Waals equation, that equation you need not know how to derive it. This is the equation. Just to remember, just to know only, in your syllabus it is no need to derive this equation. P pressure, A is the cross-sectional area, V squared. Sorry, P is the pressure plus A is a constant, V squared. V is the volume, V is a constant, and R is the universal gas constant, and T is the temperature, right? 4.4, kinetic theory of gases. Now, kinetic theory of gases, again, you know the gases are always having very weak intermolecular attractions, forces. Therefore, they are free to move here and there, so that they are having a velocity, right? We have velocities for every direction, different velocities. So, and that I told you in the first unit, the gases, we can see the behavior of gases using macroscopic properties, temperature, volume and pressure. And also we have microscopic properties like motion, velocities. So we are using these microscopic properties. We can see the behavior of gases. The kinetic theory of gases are based on this, right? So the kinetic theory of gases, kinetic molecular theory states that gas particles are in constant motion and exhibit perfectly elastic collisions. All the collisions with they are having the molecular collisions and also collisions with the wall, all are totally elastic. Kinetic molecular theory can be used to explain both Charles' law and Boyles' law. The average kinetic theory of a collection of gas particles is directly proportional to the absolute temperature only, right? Now, when you are learning this kinetic theory of gases, we have few assumptions. Those are gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. The molecules can be considered to be points that is very possess a mass, that is point mass, but have negligible volume. They have a point mass but not volume, negligible volume. Gas molecules are in constant motion in random directions and they frequently collide with one another. Collisions among molecules are perfectly elastic. Gas molecules extend neither attractive or repulsive forces one on the other. The average kinetic energy of molecules is proportional to the temperature of the gas in kelvins. Any two gases at the same temperature will have the same average kinetic energy, K equals half mv square, right? These are also the same, that the gas is ideal, right? No collision, no volume, negligible volume, and only point masses, and no interact with each other, right? Collisions of the molecules with the walls of the vessels are elastic. Gas molecules move constantly in random direction with direction of speeds. Overall, they have an average velocity. The average kinetic energy of the gas particles is proportional to the temperature. Right. The kinetic theory of gases, this equation also, no need the derivations, you have just to remember PV equals 1 over 3 mn c squared bar. C squared bar is the root mean square velocity, right? What is this root mean square velocity? I'll explain it later. See, now in this equation where m is the mass of the gas molecules, capital N number of gas molecules at pressure P, and volume V, and C RMS is C's root mean square velocity of the gas molecules. Now, if we consider that motions that are everywhere, right? All directions having different velocities. So, if we get the mean velocity, that will be sometimes 0 because of these directions. Therefore, they have squared it and divided by the number of molecules and get the root mean square velocity, right? Look here. Now, different kinds of velocities here. In our study of basic theory, we come across two kinds of molar velocities, that the average velocity and root mean square velocity. As I told earlier, if you take the average velocity, V1, V2, V3, V4 and divide by the number of molecules, sometimes this can be plus, this can be minus, and this will be 0, right? If you get the squares, V1 squared plus V2 squared, all are positive, and divide by the number of molecules, and you will get the square root of this. This is called the root mean square velocity. Root mean square speed. Now here simply the sequence root of the average velocity. Why? Velocities are plus and minus, so average would be 0. Squaring first give all positive velocities. Taking the squares give the average speed without direction, right? RMS. Then root mean square velocity means square speed is the measure of the speed of particles in a gas, defined as the square root of the average velocity squared of the molecules in a gas. The root mean square speed takes into account both molecular weight and temperature, two factors that directly affect the kinetic energy of a material. Kinetic energy of a gas molecule, right? This is the kinetic energy of a gas molecule. 3R divided by 2 NaT. K average kinetic energy, right? And R gas constant, that is we found it 8.314 joules mole per Kelvin, and Na Avogadro's number, right? This is the Avogadro's number. T temperature measured in Kelvin. You can derive this equation like this way. Vrms equals square root 3RT over m, right? Where Ke kinetic energy half mv squared, and where K is R over Na. When you go and substitute it here, then from these two equations, K equals 2 over 3 RT Nu over T. And if you want, you can get the kinetic energy like this also. K equals 2 over KT, or K equals 3 over 2 RT. Right? Then, the distribution of molecular speeds. The distribution of molecular speed is given by the Maxwell's-Boltzmann distribution. Here see the Maxwell's-Boltzmann distribution. This T1 is smaller than T2, right? T2 is here. T2 is smaller, less temperature. This is the high temperature, probability and velocity, right? Each particle has different speed, and each collision between particles changes the speed of the particles. Right? So dear children, thank you very much.